Yeah, there we go. Hey, no. Hello, Newbeck. I'm Matt Taylor, and this is a live stream from our HTM Challenge Community Meetup. This is the whiteboard room, and we've got a bunch of people who are already here. And if we have any interesting whiteboard discussions, I've encouraged everyone to have them right here on this whiteboard. So hopefully this will help us share some of the ideas that are percolating here at this meetup with the rest of the community. And I'm just going to leave it on for hours. So it may be dull in here for periods of time, but I've done this before, and at least I can take the nice bits out later and put them together for people. So that's what this is.
So it is actually recording.
It's recording right now. Come on, Felix. This is Felix Andrews. You can say hi. Everybody loves you.
I don't think anyone's watching yet, are they?
No, but it's on YouTube, so everybody's gonna watch it later.
Right.
It's live streaming. If you go to that YouTube page right now, you'll see me 30 seconds ago.
Oh wow! So we're gonna look like that.
Yeah. So we're gonna have discussions in here. I'm just gonna leave this on. There's Pascal. Pascal, say something so I can make sure I can hear you. No. Hold on. Nothing yet.
He keeps hitting delete, but you're still there.
All right, we're just doing a little bit of live debugging.
He laughs like 30 seconds later.
So my sound is working. Okay, my sound's working, Pascal, but I can't hear you, and you're not muted. So I don't know. I can see you pretty well.
Is this the speaker? Is this the headphones?
That's output to this here, and I just tested that worked.
Did you look at your output to try going to system prefs?
You see
Default might be wrong.
Built-in output. Save. Let's see that. Okay, can we try again, Pascal? Oh shoot.
No. Go to your system prefs. Try the.
Oh, that's where I just was.
Oh really?
Yeah.
I didn't see that.
Output is headphone port.
Okay.
And I can hear it.
And can you
see?
Output volume?
Yeah, I hear you.
There you go.
Yay.
Yeah? Okay.
Yeah. All right. Oh, he's took his headphones off.
Right.
Okay, so proof of concept. This worked. All right, so this will be like community chat, pretty much, with the whiteboard bonus.
That sounds good.
Cool.
Right.
What time is it, by the way, at your place?
3:11 p.m.
Okay, nice. Guess what time it is here?
2:11.
Yeah.
Yeah, 2:11. Berlin, right? Berlin time.
Wait,
Right.
it's 11 hour. Wait, what? 3 p.m. to
I don't know.
No, wait. It's 12:11. Like 12.
Conversion.
It should be 10 a.m. there.
What time is it here? It's 9 hours difference.
Okay.
I'm still.
Hello, Matt.
I thought it's 10.
Andrew Berger.
Okay.
Yeah.
But where are you from?
Canadian?
Who's that?
Nice to meet you. Did you come
What?
along?
Sorry.
Yeah.
Who's that? Hi.
It's Vancouver. Awesome.
Where are you from?
So I was just telling you
Unless
guys,
Germany is different from Austria.
I'm live streaming this room,
Same time.
this whiteboard, and we've got Pascal Weinberger hooked up right now. But I've offered anybody in the community who wants to connect and like chat here, and it's all live streamed to YouTube and whiteboard. So I'm hoping you guys take advantage of that. If there's any opportunity to, please do, because technologies are friendly.
We're all skillfully ducking the camera.
Yeah, I don't have any rules.
So this is pretty much like mingle networking time. So anybody wants to mingle network. There's beer in the back. They're still setting up snacks and stuff, but I'm sure you can go grab a beer. But you've got free reign of the office. So I can give you a quick tour. The desks are that way. It's over.
Hey.
Hello, I'm Marcus.
Hey.
Just gonna check out their office.
Sorry, we're
Hey, can somebody take me?
I'm gonna grab.
Can you take me? Like.
I'll email you one.
to take the laptop. No.
Yeah, just take the laptop with you. Or don't. It's okay.
I think it's fast. No, it's not fastened, but it's probably better if it gets left there. Hello, just introducing myself. I'm Andrew. I have not contributed anything to the HTML challenge. Right. So yeah, I'm just here to kind of learn stuff. So,
Cool.
Beer too. Oh, someone will be back soon.
Okay, cool.
That's too bad everybody left. They're all just mingling right now. Hopefully, when they start having deeper conversations and they want a whiteboard, they'll come in here.
Problem typically I find boils down to that of just having two implementations of the same thing. So it starts off, you have your idea, you have your experiment code, you build something, you put into some production code, but then there's this wall between them, and then those things can easily die.
Interesting. Hey Pascal, if you can hear me, I think I'm getting an echo from you playing this video.
What did you say?
Were you talking earlier? Was that you?
No, I'm like listening to the live stream of that conference in San Francisco.
Oh, okay. So I was in the other room and I heard something coming out of here, and I thought, and you weren't on it, so I thought maybe it was just some weird echo feedback, which has happened before. So I was just checking.
Okay, cool.
Okay.
How are you doing?
I'm gonna take this Ethernet cable over with me. Yeah. All these guys are coming. Terry, hey, what are you about? Was that created? I'm trying to make my own t-shirt. Oh, me and Terry?
He is the Jeff Hall. Artist.
Isn't he an name tag? You see it. Just right across the street. You ready?
I am now ready.
Okay. Hey, I wrote an agenda on the whiteboard there. Feel free.
Great, Good. Where are you staying down here? Where are you staying? Is that what you usually say? Yeah. That's right. Like, you kind of know. You're good. Yeah. I know it, but okay. The second is not money. Look at a beer. Beer's there. Hi, I've Christine. Hi, nice to meet you as well. He's the one that designs my okay. I love you. Did you guys see it? Okay.
Great, thanks. I was told I can do stuff here, so. I had to see myself.
The other person, Christy.
Yes.
Where's it? Somebody said you have it?
Yes.
That's the same idea.
Yeah, I saw you over there.
Yeah. You had you were, yeah. I did. Yeah.
Oh, it's super cool.
I was gonna ask you if you found any interesting ones, but I figured it's so busy.
Yes, so I found some really good.
Yeah, I compared. Okay. Are any of these world data sets? Yeah.
Some of the best data sets were weird. I'm looking for things that would.
I only learned about it.
Oh, I'll talk about it. Not really tutorial and introduction, but I can see that.
This is usual schedule for you.
No.
Okay, good.
I have a plan to get more people in here. I'm going to put the cheese and crackers in here. Okay, cheese and crackers are in here. I should probably move the beer as well.
We don't have one beer cooler. Yeah. Take water out. The only other person that might have stashed it, but it was on the shelf. I don't think it was. Sure, I think I can show. Yeah, Mary Ann, say. Well, I didn't see it. That hotel room, I never got that. I never good thing we got great. They were more cost.
Sorry. This cooler's really wide. It might take a while, but it'll work. I'm gonna invite myself in the meantime, so I can walk around. Let's see if I can get some like action shots or something. See if this works. Join. Trying to figure out how to join. You're being recorded in here.
Oh, you are?
Yeah.
So be careful.
Yeah. If you don't want to be recorded, don't walk over here.
Okay.
I should have gotten invited to this thing.
Well, thanks.
Hi, Pascal.
Hey.
I'm trying to figure out
There. Yes.
if I can, like,
There, how are you?
join the hangout and just walk around the room with the video camera. Find out.
Good idea. You should be able to do it in principle.
I should. Yeah, I agree. Invitations. Got no invitations. That's. I just invited myself.
I guess they don't like it.
I always get invited when I invite planners. Let's try this. Yeah, there it is.
We would need a robot to drive around and with a camera and things.
I think I'm gonna join the call. Okay, I believe it. Hello.
Yay. Hey.
I'm trying to. Here we go. We're doing a Google Hangout. This is Marianne. Hi, Marianne.
Hey.
Oh, you don't mind being on YouTube, right? Okay, you're on YouTube. Anyway, so I've got like a live hangout in there with a whiteboard. And I'm trying to get people to go into that room, but so I moved all the beer in there. I moved all the cheese and crackers in there, but they're not quite thirsty enough. I'm gonna walk along. I will eventually. That's what I'm gonna have to do.
Yeah.
This is our office, Pascal.
Looks messy.
I can't hear you very well, so I'm just going to turn the volume down. So we do have quite a few people here. Hey, everybody, wave hi to the Numenta community. Hello. Thanks for coming. So I don't know if you noticed, but I moved all the beer and I moved all the cheese and crackers because you're all congregating in this area, and I wanted to try and move you down towards the the whiteboard areas where we're doing a live stream. So just letting you know, if you can move this direction, it'd be great. We've got 2 people connected right now. If you want to go chat with Pascal Weinberger, or I think Richard Crowder was connected earlier, but definitely Fergal and Richard will be on later too. It's working. Say hi, Jeff. You're talking to the community.
Oh my gosh. It's streaming live on iPhone?
Yes, it is.
So
which is user?
It's streaming live the whiteboard.
How much streaming? I was just talking to Surya. He wants to do it like one of these braiding plants and cover it in head. And he wants to like get the human being pick for like the next.
There's someone who did that theory about this. Someone who opened his like put the code, called it something and then
No, he wants to live it in permanently. It's a permanent. It's like he wants to be like on the street too.
Interesting idea. I'm gonna say hi to Jeff Full. This is Jeff Full, everybody.
Hi, Jeff.
Yeah.
Yes, you guys are the cool guys. Yes. Eric has done a good job asking questions recently.
We're trying to get people to come down here.
Donna, do you mind being on YouTube? Okay. This is Donna Dubinsky, our CEO. I'm just, the community is going to be watching this. It's live streaming to YouTube, so.
Sounds really fascinating so far.
Dancing in front of the camera.
He's sneaking some food. That's
I moved all the food and the beer in there, so I'm trying to get people. Yeah. Okay, I'm gonna sign this off for now. I'll be on later.
Who are you? Every time I meet anyone, so, and then they'll say, oh yeah, but it's not stressful.
No, I met one who's not such a great circumstance for that time, but she made a call very clearly. No, it's not. It's not. I've never ever heard of it. Oh, yeah. I know, but there you turn and said, I can't speak English anymore, can you speak French? Oh boy, now we're really in trouble. If we resort to that, we go straight in the bottom. No, I should make you practice with me once a month or something.
Sergey's gonna come in and say hi to Pascal. Pascal's
who's
on-
here?
Yeah, he's, I don't know if he's connected, but. Hi, Pascal.
Hi,
We were
Pascal.
talking-
Pascal.
And who's Pascal?
Oh, that's-
Where are you, Pascal? Oh, there we go.
There is probably.
Where are you, Pascal?
In the.
These like locators?
Oh.
Frankfurt.
Frankfurt.
Oh, Frankfurt,
Just
okay.
from the tap.
There's a tap. Okay.
Well, I can tell you all about what's going on here. We have grapes and beer, so that's excellent.
Grapes and beer, what a combo. And crackers and cheese.
I've got water here, so
Ah,
Easily worth the trip to San Francisco.
easily.
Numenta guest.
let me see what I'm gonna do.
Password is Newport.
How's
So
life?
yeah, I hear good. I hear that you want to put electrodes in your head.
Yeah.
For real?
I'm not going to be the first person to get the electrodes.
Did you read this article about the guy who tried to do that and then?
No, but you know, like that's kind of the funny thing. Everybody I met like is super excited about the idea, doesn't understand the technology, right? Everybody who like the transhumanist community, they're pretty bad at it.
So he is a neuroscientist and he did that because he wanted to record data from his motor cortex.
Sorry, it's just.
And couldn't find any more ALS patients that were just that was still at the point where they could execute common. They were too sick, so he decided to do it on himself.
Yeah.
He went to Belize, he got surgery, and he wanted to leave it for a long time, but they got infected and
Well, yeah. So infection is actually the biggest risk, but statistically it's super unlikely, right? So about 100,000 people have brain injuries, right? The thing is, we have them for Parkinson's, and they're really bad microbes. They just like you put a wire in, and it sends like 30 hertz, and that's it. No chips. Right, the chips is a chips are a very recent development. It was mostly developed by DARPA, the recent surveillance program, and they're really, really cool. And they work amazingly well. The chips are surprisingly powerful. They can run basic machine learning stuff on those chips inside the brain, and battery lasts for a long time. And yeah,
So that's what you want to try with this one?
well, yes. So there are two initial applications, right? Subcortical stuff, which is basically you have an app that lets you control your emotions, right? That's super simple, and that's what DARPA already has. They have that. It exists.
To control your emotions, like as in relaxation or something.
Well, they use it to treat depression, but same thing. Realistically, same thing. You're depressed, you press a button, you're not depressed. That's basically then there's the cortical stuff. The cortical stuff is interesting in that it allows you to read from the cortex. The cortex learns, so you can learn to control electronics. That's what they use for neuroprosthetics. Right? The thing that bothers me that hardly anybody seems to realize that if you can control prosthetics, like you can use the same mechanism to control electronics. Right? So the setup I have is basically you wear a Google Glass. Has a heads-up display like you find in video games that you look at something and you look at the microwave, it says press A to start microwave. You think that command A runs through your phone over IP to the microwave transmit, and you can microwave, life is difficult. But yeah, I think that would be really cool.
That's a cool, definitely a cool app. So did you meet Pierre during one of the meetups? Do you remember Pierre Carachu?
I don't think
I
that
think he was at one of the hackathons.
maybe, but I
So this guy, when you read the article, I want to do this too.
no. So honestly, the limitation is not like I have way more volunteers than you would imagine. I have like a lot more volunteers than I can accommodate. Right?
Yeah, you want to do it. Not on yourself, but on someone else.
Yeah. So I won't be the first one. The reason for that is not actually the risk. That's Biggest problem is backwards markets that start with first investing. I want to get the net
Companies,
which is projectable size. That's all that's right. You get a link. I think it's yeah. I can't remember the I was just wondering how my work. It's kind of the shit like that. What legal system.
Wait, that's me.
Yeah, here like the well, several besides the
like in your living room.
Well, I think it's yeah. Well, maybe in my living room, but like
But 4 out of what? 13.
So,
I don't know if you've ever. Just like ACL 12.
track renewal.
There are 2 that are
added
added
up
up
there,
like the
But
playlist.
so usually I remember we talked about it, and
Is
it's very limited.
sort of
very
constrained at a common list.
I don't really think
Where,
cheese enough.
every
Even
function is
for
little
germs,
and in order
your
to,
right hand
and you
on
basically.
Oh, I
added
think
it.
that's using the job.
No, it isn't. I didn't really
That's sort of
like
stuff
it.
you can do through sitting down with like.
Like actually.
ECG or E.
This is sort of like based on a month here on like
Silver, interaction here, is about
More consultant.
I think about 800. It's enough to me. Difference that also the home and research. I'm not sure yeah.
So cloud sonar.
Thank you very much.
That's gonna be fun. We're gonna get a job under this.
So
So are you, is it like
I'm separately on the I was hard. Like and I was like everybody else was there. I would like for my PhD,
I think I have one guy pretty interested. Use happy.
So you know the times are like
Yeah, MIT is.
They don't hang, they're not
It's okay. Yeah. So where are you from originally? I didn't know what it He's an awesome. Yeah. Right?
Oh, man.
That little, oh, man. Yeah. Is it Olaf or Olaf? It's Olaf. So they, oh my
All hands.
Did you say Olaf like it's from the now you say Olaf like it's from like it's It's like my daughter's house. She was originally from Russia. I got to her. A lot of Marines, for whatever reason, people that have trouble hearing, and they get Korea, they try all these questions. So I got to the marina, like where they keep boats. And that's
This byline that is actually now, you know, really, I mean, the Golden really put the name on the map.
Yeah. When did you realize that? Did you see it or did you start hearing about it?
So, two things. First, I got this, the key is memorable. And a friend of mine said to this boy, the snowman.
Right.
I didn't know what to make of it.
Yeah.
Then, about a week later, last year, this little girl turned around and and that's actually a funny character, I have to say. Yes. Yeah, true. I really ordered this as to be associated with that.
Yeah, it's better than being the villain.
Right.
So have you tried playing around with them? Do you feel stuff yet or no? It really is. Okay, that's all right. Yeah.
That's the really I
Okay, I just unmuted, but it's really loud in here, so I'm not sure it's gonna help. We're gonna have presentations in about 10 or 20 minutes on the other live stream.
And we say that you can like do improve which one do you want to not the problem so it's not like so sorry.
It is. Let's get curious. Alright, so you were saying
we put the answer, all the amounts, we take all the amounts. So you have different like paths. So you have to get one, get a hundred. So usually you get an answer the same thing. So once you get top one, you get so we answer that question like that, and we know that we can do ourselves. But we need, we were running out of time, we need more time, we need to talk with the people that.
I was so happy to see some laptop for myself.
We just like thinking of Stop. Well, that's the thing. Because that happens a lot. Well, the more it happens, the more we learn it. That's very that's the worst case for us. It's nervous, you know, and so really other classic techniques in my area.
Yeah, we don't want to buy everything. So do this last
My daughter,
So we're in the cheapest time. We are learning this kind of
Really, I have been on a tour. They just have because you know everything else. where the papers go and everything goes to the past. We'll provide
They should track tax.
I have all of that.
Actually, I
Tons of interest. No one's talking about this. Streaming data is really hard.
We're
ready to get
Yeah, I turned it on my friends.
Okay.
Over there.
I read college and go flat.
Oh.
Yeah.
I don't tell them not to.
Great job today, Susan.
Oh, good. Yeah, it seems like we got a lot of interest. I didn't know they were gonna live stream it. I was like, it's a change, like, oh, I watched it.
Can I have your attention, please? Can I have your attention, please? Can I have everybody's attention, please? Sorry to interrupt your conversations. We're going to start our first session now. It's going to start with Donna talking about business opportunities with HTM. So if you're watching here, switch to the other live stream. So yeah, if you're interested, please go take a seat or find some standing room. Find somebody's desk. You can sit anywhere that there's a seat.
Okay, so I'm curious about the two other questions.
Because of that,
That's all I that all that song something.
Enthusiastic. Yeah.
Changed my life.
It's not an espresso or
Tried to get some earlier, it was just too crowded. Yeah, it's garbage. It was really great. There were some people who came immediately over after your talk. Very clear that they were inspired by the talk.
Oh, good. Good.
And one person who I talked to earlier in the day ended up coming back to follow up. Right, because they saw the talk, so.
Science or intelligence, it really is fundamentally about what you're doing. So that is part of our mission. We also have a business mission to build technology on it and to enable others to build businesses that more technology. Big platform believers, Jeff and I worked together for many years, we've done multiple platforms through our history, and I think probably one of the most compelling experiences creativity and the crowd strength of the development community and how they do see things and happen as a result. So that is very much a part of what we're trying to do. It's particularly important in this case where our technology is very broad. We know it's very broad. We know there's no way we can do every possible app out there that what we want to do. So it's perfect opportunity for a platform where we can take specific problems and address them. So that's Together, what they add up to is covers all the sides. So, rather than add back my history, yeah, it's such a privilege in the room, looking at big generations of manual computing, smartphones, and now we work on intelligent computing. It's basically something as big as the next generation. So, all this time. So, on the business side, it's been 10-year odyssey. We have tried lots of different business models, business structures, how to help people sell. We thought through a peer platform approach early on, customers support, direct enterprise sales, we actually had sales reps, I was calling on big enterprise. So we've done that ourselves, we have done Rockford, less, we've got sample applications to inspire people. And where we are right now is an interesting notion of a tech transfer model. I'm not going to explain it now, we'll talk about it more in a few minutes. But really, it's something that we really want to have a platform that is strong. We want to figure out a way to do it in such ways to enable other success. So that's the cause of saying this. Now, open source is an interesting and important piece of this. It makes it a bit complex to manage, but it's just critical to start working. First of all, it enables transparency with everybody. That we think is very important. That, by the way, makes it so much fun to work on because instead of coming here and saying, us saying, oh, we have to work on our I can't try that or whatever. Well, we haven't touched, let's go look at all the source. Ourselves. That's confidential. Share our research doesn't go share everything. So it's a philosophy of total transparency. Researchers and academics working hand in hand. So they don't have to come talk to us. They don't have to engage with us. They don't need permission. It's a wonderful way to just let them go as much as they want. But we thought a lot about this with the open source. Does it negate our ability to build businesses? How do we keep the commercial opportunity alive while also having all the advantages of the open source? And that's where we're getting this tool license structure, which enables people who want to keep it proprietary, enables them to come to us for a commercial license and keep it proprietary. And what they want to do is build something that they can own and not make available to them. So I think where we come there's questions on this, and you can feel free to interrupt. So what is this kind of interesting new business approach that we have? It actually fits small companies and startup companies. It isn't a business approach that's targeted at big Google use this or Apple use this or big companies. It's much more small company. Technology that we really think is going to take entrepreneurs and creative individuals and small teams to be able to grab this stuff, figure it out, apply it, be nimble, adapt it. And so it's starting very much towards the entrepreneurial audience. So first we created sample applications to inspire people to build things that people can build. So for example, I'm using the geospatial tracking as an example. We were just talking about this. So created geospatial tracking application to show up with automobiles. But there's many ideas of businesses that want to build on this. I focused on initially the kid tracker. We wanted to know if there's a flat tire on the bicycle on its way to school. So a kid tracker is inverted movement. Truck management. Transportation agencies. And these guys here did one of their HTM Challenge out with tracking aviation. It's a great example of one geospatial, taking our sample application and technology and how to apply it. So that's what I'm doing with sample applications. We're not going to commercialize them ourselves. We've learned that there's a lot that goes on top of that to build that into a commercial grade solution. So we're not doing that piece of it. And what we do is licensees to commercialize those products. So what is that business model? I'm calling it a tech transfer model. It's like there's research organizations like SRI as an example locally that create technology but don't commercialize themselves, but spin it off. And that's what we're doing. So we have this opportunity where broad license to our technology, small ownership and small royalty, and start a company that totally aligns us in terms of the desire of the company to succeed. We find it very quickly we have this interest in all these companies to succeed. Kind of we're a little yet it gives the company total freedom of movement to go as fast as they can without having to worry about what multiple licenses they're going to get from us. You know, we've got a clear path and it just run. And we know how challenging this is going to be. So that is that's what it's just good. So we put together this package that has these elements in it. And it takes a bit of work, it takes a bit of documentation, it takes a bit of work. So because of that, we created an application process in order to actually work with all that. It's really helpful if somebody has some domain expertise or somebody on their team with domain expertise where they can say, well, I know this field, I know this would be a great idea to apply this particular. So we've got two of these partnerships so far. Avid partners, saw our AWS product at a AWS show. He was really interested in it. He was a successful entrepreneur that had built a couple companies in this IT DevOps space. He knew that the businesses were not being well served by the current technology, that they just wanted the false positives on words and not getting the right words. So he approached us and said, is there some way I can license this? Talk about this model and he got excited about it. So he is now taking the rock product, which is in beta. He's just finishing his beta just this week. He's doing all sorts of integrations, dashboards, he's doing audit trails and access levels. He's doing all kinds of things that don't do commercial product that are non-HTM in a sense. So he's taking the HTM work and creating the product around it. And we're very excited about that. I think he's got a possibility there. Portfolio, many of you know, and has been working with us for a long time. And one of our earliest partners is focusing on natural language processing. They have a huge amount of interesting work going on, and some real enterprise clients that are working right now. They now done a deal with us. They are offering some licensing into technology. So they're another example of partner. So for us, we're really interested in there are other people who want to make companies like this. Discussion underway, not that it's ready to be announced, but just to give you a flavor for them. A couple of people did our stock security candidates. We did the stocks. Stocks product. I think it's all just hard to do. And we have one maintenance for a heavy industry. Tracking some sensors. And we have someone who very hard on health, a physician who does manages pulmonary disease and pulmonary disease. So we have a lot of things bubbling around like this, and in general, we're finding a really positive reception to this idea of structure that lets people, just go for it. So I think that some of the best opportunities here are the ones where we have worked on some of the example applications, where you can see good examples and start at a level where there's things to work on. behavior, to me, that is a big opportunity. Today, people are working mainly about things like intrusion detection, but the notion that a production person on the network is behaving in an odd way is something that you don't do. So, I think opportunity. A lot of health sensors, more and more health sensors. Wherever you see sensors and more sensors, that is a great place to look for those data. Sensor stream data. I think in manufacturing, we've not had a lot of work done in manufacturing, but I hope it's now instinct is that there is a lot of opportunity. So what are the characteristics of all these things? Time series data that has some real structure and work. This has to be history of well. Can't you predict the prices of stocks? Well, I don't know. Does the price of stock have no structure? We have to do a really good job on stock law. But that's so clear about so the time series data matters in the real world. The sweet spot in terms of the sample rate, 1 in 5 minutes. So if it's super fast, it may be difficult for us to aggregate to slow. But if it's slow, you won't find patterns that are too long. Something that samples once a day is not going to be interesting. But as I said, when you think about what are the right problems, if you start with the sensor, think to yourself, what's the data, what's the sensor, what's the streaming data source? That's right now, in terms of functionality, anomaly detection is definitely the easiest. We spend a lot of time on anomaly detection. Just announced this week that we implemented an anomaly benchmark. Sometimes return series is going to be speaking about it. Keep running for it. You should definitely look at that. It's very interesting. Again, it's got great comparisons to other techniques. And so anomaly detection is where we are the furthest in terms of functionality. But prediction is not far beyond that. We effectively have to do a prediction to find an anomaly anyway, so it'll just take a little more work on your part to expose the prediction. But prediction is very good. And, probably the number one thing is you got to get the data. So that's often one of the biggest issues is get the data. We have somebody talking to us earthquake sensing in Mexico, and we have the sensors and we're excited about it. They said, well, what's the data look like? It is, well, it only transmits data when it's earthquake. It's like, well, we need more data than that because we want to know what's normal in order to know what's not normal. So, we scramble around trying to find other sensors that actually so, you have to kind of look at the data and say, look at the data. We are working on an additional tool that I wanted to mention. There's a champion of this back there. We haven't announced it yet, so it's just for your information there. I guess we have this new project underway. And now, he said having these tool for testing your own data. Some people here are very Linux savvy, and it's not difficult for you. People who are less Linux savvy, we thought we would try to create a tool that lets you take your data, run through it, and see if you can find so that can be available after the first of the year. It's not a tool for deployment, so if you go down into Numenta and other ways to actually deploy it, but it should be a much faster vehicle for understanding your data and looking numbers and collecting and finding data. So I want to let you know that's great work underway and some stuff. So, as I mentioned, we have a bit of a license application process. If this is something we have all the details on our website under licensing guide. Write us if you're trying to salesconnect.com. Best applicants are people with domain expertise, technical resources to do their own experimentation. We're not going to be doing experimentation for people here. We don't have the resources to do that. Access to the data and some business expertise in building a company, particularly a startup. So as you look at this, if you think it's of interest to you, you might want to think about a team that has those kind of people bring together those in Also, by the way, I'd like to know, we may see some consulting or employment opportunities along the way here, because sometimes if people come to us and say, well, I could really use an engineer who knows how to work with this stuff, how would I find them? So we have set up a list, and a lot of that, where, you know, to the extent we hear about those opportunities, we're going to listen to them on that list. To the extent we have requests, we're looking for people, hey, you know, I'm going to come this way. Feel free to use that list. So that's really for more business folks. So that's all I had. So, you know, we're ready to get going. We think this technology is ready to be commercialized. We're excited about more iOS business goes right. And our friends at Apple Partners, Casey Pinker and his team. So we would love to have more people working in more areas. So we welcome any inquiries along this. So with that, I'll open it to questions. So any questions or comments? Yes, we have seen an increase in interest, particularly over the last couple of years, I'd say. And, you know, we have people kind of steady stream of companies coming to us saying, we hear this is important. Tell us why and what we need to know and what we should do. You know, we can do a little bit of that, but we actually can't get there to something useful, you know. So I think it goes a little bit as just general education, tire kicker, some people say, all right, we're gonna, you know, provide a little bit of information, but we don't really look at those as promising for the near term business. But we do get a particular number of those. And then we get, you know, more and more people who are just kind of showing up. We don't know if they're out there working on social media. They're showing up doing interesting work, they've gotten something to work, and they're saying, okay, now we're up to it. And I've seen that. I find those are two very different motivations in there. The first is much more, is there something going on I'm going to miss out here that I better find out about? Second is I have a problem I want to solve, and I've been unable to solve it, and now I'm, you know, I've heard about this interesting technique. Is this going to solve it? Well, part of what I answer that, right? Natural language processing. You know, I think that one of the beauties of HTM is that it's so broad and that it can do so many things. And, you know, I was just remarking earlier that one of the things I love about the HTM Challenge, they're all about different things. They're assisting more technology, all those things. You know, I'm certain there will be apps that will catch the public imagination, whether it's, you know, more or less rapid or accent, but I do think there will be apps that will capture the public imagination. I wouldn't be surprised if it is natural language, so I take that seriously. I think when you think of an app where you really get it, you say the brain can do it, and you can't do it today. It's more like the brain. I think that's what it's very easy to understand. So I can easily see that being captured. But literally, I think, you know, we're going to see breadth of this that's very interesting in terms of library. You know, kind of saw that when we did the first really pilot. It was so interesting that tool out there. And, you know, these people were tracking wild animals and Africa. You could track it, figure that out up front. Never would have that one. So I think there won't be a dominant killer app the way there was in PCs. But I do think there will be certain apps that will have some interesting technique. Yeah. 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 Yeah.
Any other questions? By the way, you can get data for wild animals there. Oh, they've got trackers. There's a public database.
Yeah, I have all the details of this document on the website, but basically the idea is a broad license exchange is very small, you know, like a lot, I think they're essentially, phone forward. You know, probably the most unusual thing is that we're not saying we want, restrictive licenses, we're not restricting domain. So even if, we're allowed to do natural processing today, we find that there's an application that is a bit different from natural processing. I think I looked at some very interesting things for dealing with, situations where there's lots and lots and lots of factors and they apply technique. We have not let licenses to let the licensee go wherever the market of the technology takes them and not worry about outcomes. At the same time, we have not learned to do this. So we're at the same time, we're saying wherever we want, we're also saying we can license wherever we want. Now, it's not in our best interest to go license 500 people, so we don't think that's fair. But we also don't want to sort of carve up market spaces and deal with the tension and laws and boundaries and stuff like that. So from that perspective, it may be a little bit unusual. It's broad and it's not exclusive, and it's, basically saying, you entrepreneurs, you go for it, go do the best you do. It's all there. It's not restricted by geography at all. So wherever geographically it takes you, it's not restricted by markets. It's really, it's quite surprising for us. We're not focused on this, but we're focused on us. Like, I can like focus on technology. You know, even before the downstairs were created, my history tells me there's some good opportunities. And I would love to see some really work on that. Back in our first generation, so we had to work more. We did have a couple of things from people on some very creative stuff. There was a guy who did dance game, and there was learning kind of these dance moves and how big these figures to these dance moves. And I thought it was very, very interesting. Teaching the contest, remember, we looked at the concept of really out some very clever game ideas. So, I mean, I think I understand what you're saying. It's really great to create, really get some actual opportunities on the game side. But as far as I'm concerned, hey, it started now, what we do now, and learn and boy, build some products. I always one of the first places to see techniques and games. Oh, it wasn't quite like you said.
Other than that, it's going to take me probably 5 minutes to get the next presentation set up. Presentation is give me 5 minutes. I expect to yell at you guys in 5 minutes.
Well, they kind of like, Jeff was talking about it. Nice to be back. Pretty good. Super busy. Super busy. I'm very negative. But yeah, I'm doing busy curation of electronic parts, trying to get basic. So we're going to aggregation and classification of points, systems, capacity. We want to be able to amplify, oh, this was form fit function. Swap it out. How do you do that? It's based on attention. And then there's also this big description, and just kind of like a drop. Yeah, other than that, it's more vanilla.
Got somebody here at like 2 a.m. ready to give us a presentation, so please come sit down. Alright, so let me introduce to you Richard Crowder. Richard Crowder is he's been working a lot on our Windows development effort with this actually contractor and customer, specifically on Windows builds for work. Great progress with this. So, here it is. He's got some presentations on audio signals to HTM. Very interesting topic for me as well. Remember our last hackathon, we went through big using theory sessions, so things are probably really new. And Richard is there. He's been doing a lot of research since then on signal analysis, and this is a presentation that he's put together. He's made it into a YouTube video, so we're going to watch the YouTube video. We have Richard live. We can ask questions and have a discussion about that. So Richard, anytime you want to break in, tell me to pause, go for it, I'll be right back. Otherwise, I am just going to play and try to test the audio.
This slide shows the processing hierarchies that approximately the aspects of the cortex and processing experience and concentrating on the organs. This occurs in cells and breaks down. Includes processing for things like horizontal segregation, segmentation, structural analysis, to see on the side, the processing foods at this stage. together to 18 response per second. So this is processing really processing because before any other high level processing content analysis, this is just analyzing so I was doing when we listened to practice. So as you can see, this slide went to the speaking, so it's listening to the microphone. To simply jump to what I would be able to do in audience. Through microphone, you can see the same in this case is the different times too. The signal will get very clouded with all sorts of things. So you can get back response from the past. Serious, it's also continuous. If you look inside the human, it's essential to these you should be like each year's next to
Try to turn it on.
Two things, right here to the left. The three you can see are related to one's rotation function. Practice in the spine. That's actually called the spine. So here, so is practice. Spine into the side. To feel that it's sets up in some fluidness inside. It's how the spine will place heads and come together. Standing around the house. If we take the spinal and stretch it out into, in this case, I'm not going to say a semicircle. You find that there's three rows of active cells in your sleep. Seems like it is. Mechanism changes sensory information and just makes it to something. Which is feedback information. The other excellent trying to show feedback. So, as you can see, the reports in the diagrams, which has information. Maybe these are laid out. So, two to spine. Right-hand side shows feedback, both ways, and lots of this is where this is where it shows what the Shows it's something called the universe, and that's the same. This is quite complicated. If we start from the top, it's 2 hemispheres of the text.
Hello.
It's relatively frequency related to the topics of representations used. One shows the continuous groups. So it says the persuasion. So you can see that the starting stops with this persuasion. That's so there's a frequency which you can start seeing. So if you're looking at the transition from G constant. You look at the high frequency which is letters A and D. You can start seeing motion to those high frequencies. And so looking at the intention in motion of those letters. So what you have the original signal in your representation is this. So you can start so first to witness the solid outline frequency representation is solid outline. This is created by light to see it's on the so you see how this changes over time. There's a snapshot of time to the same. This experience of this frequency. So you can see that you can hear different. One thing is success will show, which is over time. You can see which is what C forms and then much more. So it's all just that. Same things. Yeah, check it over time. So just in case, 32 minutes on. You see that so choosing to do representation, frequency. So once you got about a simple representation, it's a simple. A simple representation can get into task representation. Time has changed. The thing that occurs is the epochs see the text to an actual method to the method to the frequency. By changing the representation, it has certain features that so it shows you actually uses us as a representation fed into temporal and to analysis processing simultaneous signals. So returning to the first slide, trying to show highlights is the new process because what's happening to the government. Trying to understand as you can see, what you get across distributed documentation without people teachers every time teams series all this critical time zones and some processing critical to get this takes That's just
I thought I was going to go figure out how it totally worked. It turned out it was a whole lot more complicated than I ever imagined. So I totally commend Richard for the work that he's done on this because it's not easy. So does anybody have any questions or comments? David Ray.
Hey, David.
So.
No. So I had to take a break.
Okay.
So I had an issue with my son's school yesterday. I had to take care of. Sorry. So I kind of put that on hold.
Okay.
But
It looks pretty nice that we can do all that stuff with it. Be able to do like, we can just exclude stuff.
yeah, I got it pretty close. I figured out what I was doing wrong. There's no, I think the approach is still to pursue the doctor one.
Right, and I'm trying to figure out how we can just solve Visual Studio in a wide environment. It's like,
Yeah, good luck with that.
people doing that.
Really? Well, so what I found was, so there's no like stop DynamoDB or stop emulator command. So when I ran it the first time, because it's all running in the, like, using the same container. So the services are still running. So I kind of got distracted by that.
It's gone on. Well, that's just the actual food first.
Yeah, kind of.
Yeah.
But yeah, it's like, I'm satisfied with it. I think in the end, what we ought to do is expose the Docker host so that the build itself doesn't launch a container.
Exactly.
As opposed to running the agent.
So this is a good taste of work and stuff back there.
The image is way there, so it's not going to be built images.
Right.
So
We just have to make sure we build this Docker images that are friendly.
Yeah.
Like, I saw a trigger in the thread where we move the requirement steps to look at the stuff, and then we copy the rest of the stuff. This way you make sure the requirements are for the first. This is going to change. That's a trick that you can do that way.
Yeah.
So you have, the layer doesn't change.
Right.
For the requirements text, unless requirements text file changes.
Right.
That's an example.
Yeah, but I'm pretty pleased with the outcome. I expanded.
That's one move, right?
I expanded on my comments.
But
So I have mine for the earlier times.
Yeah.
ECG takes you.
But yeah, like at this point, the biggest downside I found is literally the fact that we have to maintain our own infrastructure.
Right, and that's
Yeah. So it's like, I think it's probably going to be worth it as long as we do it in the way that's maintainable.
Final analysis, so when you got to the frequency domain, the clear lines.
Mac and Windows.
Final signal before it goes.
Yeah.
Many columns.
But I mean, if we can get a Windows instance from ECGM.
Which is great. That's not very good.
But once you start it, you just need to run the agent.
But these are the security bullshit. Just could not download Chrome from Google. That's was a pain to just download Chrome from Google. Integrate VPCs and stuff.
I think it was actually easy. We just need a physical machine.
Type 1, type 2.
Kind of.
Yeah.
We can use the Travis machine.
Type 2 focus.
Some kind of virtual.
Well, I'm thinking for Bamboo, to integrate it with Bamboo. Because what matters is running the agent.
Right. Well, you have to run the agent from there to connect to our network.
Yeah.
Outbound.
It's easy.
So if Amazon to connect to us, you have to create some kind of VPN.
Yeah. They have that though. Yeah. But I like Bamboo.
I like it better than that because I understood it. I didn't have to.
Yeah.
Thank you. I need to learn something, and I cannot understand what was.
Yeah.
I'm going to be looking at speech stuff.
No one was there. Here's your outline, here's the job.
Right.
What the job did, here's the script.
Yeah.
It's right there.
I think probably review it next week and make a decision. The pricing is not bad.
For how many agents? Yeah, how fast are agents, right?
We can get like 10 agents for like $250, $300 or something.
A month, a year?
A month. But you can do a one-time payment for a year.
Because I saw one that you can just buy the license.
Yeah. So
Models you can get, we just have.
so that's like one agent or something. Yeah, for like 10 agents, it's like over 1,000 or something.
Which could tell you that this was working.
Yeah, especially since if you do the cloud offering, you still have to pay for the EC2 instances. So
That's hosted, right? We don't have to. The cloud?
yeah, if you do the cloud option, it's hosted, but you still have to pay the additional EC2 charges. Because they'll provision the instances for your own account.
They have open source, like, but I don't think 4,000 is very I wasn't meant to work with open source side.
Yeah, yeah, and we might be able to talk to Java and say it's primarily for open source, so they can probably meet us in the middle somewhere. Start paying customers for
Jira.
They use ultrasonic signals to catch moths in flight. It's really fascinating how they can send it out.
I like it.
Steal those ultrasonic signals to actually do trajectory analysis of the moths in flight and catch them. There's videos from the 1940s and 50s that show in cubish darkness, them flying and catching these moths in flight. And these are good further to the plants that catch fish. And they look for ripples in certain kinds of ripples on the surface of a pond. They can fly down, swoop down, and catch the fish. They're trying to help them catch them. This is fascinating to look at that. As well as plants that have apples for rice. Fascinating one to look at because they the fundamental frequency that you usually hear from the and all the harmonics, we can draw out a lot of those and still understand certain tones. They're amazing at trying to understand that.
Biology has to run with, chemistry and membranes and ions and ion channels and like that. So, and obviously flights in early parts of the brain are essential. So it's a lot of reasons that the only way that a biological issue or issue building blocks that cells are made of, you don't get a choice of putting it on. So, obviously involved in the beginning and faster than fusion. And then it was used in this process here, and then it was kept around. And so, that's what it came about, and it works. It's a very low power way of saying. Richard mentioned myelinated, unmyelinated neuron, that without more recent invention, myelinated neuron actually sends signals faster. So they basically understood, hey, I have these easy cells, they're not in the fatty cell called myelination, and they send signals faster. So, they didn't have to be a reason for everything. Are essential. May not be essential. Process. Still, we might be product.
Any other questions for Richard? Richard, do you have any closing comments?
No, sounds good.
somebody. I just sent you the link. Yeah. Yeah, we have to yeah. One of the quick remark on what Jeff just said is, I mean, I was an internship at the West Point Institute for Business here, before Sigma. You guys used this name at some point. And one of his hypotheses is actually that spiking in the cortex, especially for visual processing, is used as like a common pattern of communication, such that areas in the like columns or higher level areas in the brain that have the same spiking weight and spiking activities, they can correlate better to each other with local potentials. So that's just one thing I would draw. Okay, I'll do that. So my title, yeah, I want to talk a little bit about intelligence-based to analyze and visualize observation data using HTM technology, and that kind of just from what mentions in the book on intelligence, I kind of have basically like, you say something like, imagine that we could observe the entire Earth or have like a huge brain observing the entire Earth and entire sky with like a model brain, and that's kind of what I was hoping to go here. It's like a global anomaly detection thing with yeah, protection. So what would you do? Like there's on the next slide. There's 200,000 people dying every year that are affected by earthquakes, typhoons, tsunamis, and anomalies weather and climate data, basically. And on the next slide, there's 11 billion US dollars in damage that which are produced by such disasters. And if you really think about what these disasters are, they're nothing but anomalies in Earth observation data. On the next slide. Here you can see like just some seismic data which was recorded in a station close to South Africa, and that's just like an example for what that data actually looks like, and it's one of the time series you would think you can easily feed into in the model. And I've got some examples here on the next slide. There was an earthquake magnitude 9.0, which was really powerful, and you could actually see it in the data, and it lasted like more than 10-20 minutes of scheduling and that. You then do different component where you don't just need to strain, which we call it from strain but that's called, which are basically labels that measure the movement of the subsequent part of the Earth. And if you do a difference for that, you can easily see the thing. And what's the hope here is that there's some anomaly indicating what's going to happen next. So if you just take a look at the right-hand plot, you can, with some imagination, find that there's something moving in a weird pattern before the huge spikes. But that's nothing like regular. On the next slide, you can actually see that there was on 9th September 2011, there was a huge earthquake in Vancouver.
and you don't see anything. But what you see, like nearby is the construction site that was nearby the main measurement site, and this would use a huge amount here. So there's some complicated pre-processing required in order to get rid of things like that. The employees, the aspect of noise that you may know about, like construction sites and things like that that have to pipe down in order for such systems to be active. Next slide would be just some evidence for multiple factors to be included, like the moon distance obviously has an effect on how the Earth is formed by magnetic and gravitational attraction. So if you look at the distance from the moon and the earthquake magnitude summed up within a month, and you can see that there's some synchronicity to be seen in the past. And when the moon is far away, there's more and higher magnitude happening. And if the moon is close, there's less earthquakes happening. So you need to have like multiple input fields to actually code such information. And on the next slide, I'm just going to go briefly over the architecture I would think such a system would need to have. And this is, you basically need to stream in multiple sensors information, as well as social media and contextual information, which I've already touched on with the construction sets and things like that. You would then need to stream them into something like a view that probably a little bit more parallelized. And basically have an HTM engine with like a lot of pre-processing that gets rid of all these noise factors. And then feeds it into an HTM to produce anomalies, like give you anomaly scores, and based on anomaly scores, evaluate the list of catastrophes that would be happening. And you would then file things like, just as an work application, you would then fire out mobile alerts that would be within these areas of interest, and provide the information to companies and groups like regions, companies, corporations, NGOs, whoever is interested in information. On the next slide, you'll find like the visual interface activated. This at the moment only shows you the historical and slide information, and not really much relation to this what's supposed to be done. And I imagine I can do a visual interface where you could learn about the catastrophes and disasters that happen, and the information that has been and will and can be gathered about things like that, as well as resources to help you learn to stay prepared and be informed about disasters of those kinds. On the next slide, you'll find a visualization of the raw data in San Francisco where you guys are. And you can obviously see that the red parts of the area is really wide, and the other things like the blue and greenish layer you can see there is the accumulated rainfall over the last 30 days. And what you would kind of teach with that is where there's the rain, it's getting wide, which is obvious, but it's just some way to visualize it. What I've also been trying to do here is bring satellite data to everyday users, because if you try to get satellite data which is not from Upcast or some new company that's really doing a good job on that, basically from ESA, then you're going to be confronted with a really complicated interface where you have to download like 2 GB file format, and then plug them together and do all the like stuff they should be doing yourself, and nobody's going to do that just see a satellite image. So yes, these are satellite images and really well. And you can here like information on the next slide as well. I just encourage you to just play one with that. And it's working on mobile phones as well. Safari and iPhones are not really well supported at the moment, but it works well on Android. Just give it a try. And this is basically one of the things that dynamic or whatever it is before. In the end, it's trying to do is just take all that sensory information that's just available at the moment, but not being used for any good purpose, and if it's used, then it's used just as already been mentioned today in the past. So there were like this Mexican guy that was talking about that has seismic data, but only when earthquakes happened. So there's no use in detecting anomalies and doing like live feed processing with them. You need to have the data that is available and free in order to actually be useful, and such valuable data that it needs to be used. I mean, that's why we're using it. And one of the applications that kind of fall out of that was what we've submitted for the ESA app, which had to do with saving our food on the next slide. Because what obvious case you think about here is agriculture, where you also have satellite data available, and you with the mobile sensor to get screening data from fields to find fields within find anomalies within fields and then match them with databases. So I guess you can see next slide. That was just ESA outcome which we participated in, and we built iOS application called Gaia. Yeah, these are screenshots of it. It's still in development, and we have hopefully start a company with that and trying to commercialize the usage of observation data in combination with disease prediction. So how we are doing it is shown on the next slide. And we basically take the satellite imagery and extract from that different bands of imagery. We extract temperature, humidity, UV index, and some other data source, which I'm not thinking about at the moment, and then combine that with sensors, so small Arduino or particle sensors that we assemble that farmers can plug into their fields, and what you then have is really valuable because you can actually infer from all the weighting that you get on the surface data from the top of the plant and the sensor information that is below the actual plant on the bottom of the field. You can then learn at least infer about what radiation was absorbed by the plant, what temperature was, what heat was absorbed by the plant, or is ejected by a plant. If you put in a sound, a microphone in your sensor, then you can as well learn about insects that are in the field, and all these kinds of information are basically the time series that should have common patterns in there. Climate has some patterns in it, and day and night rhythms, which wouldn't be detected by some things that are used nowadays for farmers, which are just like in situ sensors that warn farmers when the field gets too hot or too cold or too wet and too dry. And these are all the complexities that are just ignored in the systems. The next slide shows like the first sketch of how you would present that information to a farmer, because it has to be understandable. And what we thought of was just a map where a farmer can go all these fields, and then tell us what parameters on that field, such as we can from the information we have and knowing what plant it is, we can tell the farmer which diseases are most likely to happen to that plant because the plant has been used. So you have that information. And then you would basically show the actual data to the farmer with this score, and then output your prediction of what the next expected disease might be with the symptoms that the plant should show if your prediction is true, such that the farmer can go in and check for himself your prediction is right. And once he's confirmed your prediction, then you present him with treatments and things the farmer can do in order to prevent that from being happening. So we want to either have templates of that, and yeah, we're currently looking for funding and ways to actually implement the entire system and post about that. And I guess with that, I would like to open for questions and close the presentation.
Thank you, Pascal. If you haven't tried out economic, Nostradamus.org. Pascal has a massive amount of data, and it's got really excellent visualizations really below that you can spin around and dive into. I'm just impressed with the huge amount of data. He's been doing really impressive work since he joined our community. Does anyone have any questions for the type of work that he's doing? Like he told us it all. I have a question, like, what
Absolutely.
Several different data sources, I guess, you explore all these
I guess the problem with the Nostradamus Q project is that most of the data sources you would need in order to predict, or at least evaluate the risk of earthquakes or typhoons and stuff like that from happening, is that most of the data is commercialized at the moment, so you cannot access the real-time data. And there are some archives and for certain cities, there's things that Matt has already done a good job of gathering, and there's just not the mass and the amount of data you need in order to try and rely on the system. Whilst on the farming perspective, you have a restricted problem, so you know the areas you're going to need to get data from, and then you can provide the farmers with devices that are good for actually gathering the data you need as a sample that you need. And you can basically decide on the parameters and you're not dependent on other systems. So I guess the farming and agricultural use case is one you would start with, and once that's working, and you confirm that the hypothesis works, I hope to expand on other fields. That's
Anybody else? I want to let everybody know that we have food. All right, be back here in 10 minutes. There's food and there's
You're welcome. I don't know if it's worth it, but Yeah, exactly. But there.
We need more beer.
Hey, Vicky.
Are you? I like salt. There's more on the counter.
Oh, there's more there?
More beer, and there's some in the refrigerator too.
Sure. Yeah.
Is that portobello? You guys can. There's 12 members that they're just asking. Yeah, QB Connects. So that one is slightly older. Both work. Here's some baskets, Jake. Straight switch between. Oh, that's still good. Okay. Right. So to say, and be like you pool, so you learn some template pool. So in the pool, when you have some representation, then you can say, and you're trying to get a sharp this is my well, I don't think the way you're saying it, I agree with and so that's why we're totally different. And so you have two different things that are in the same context, they're going to look the same thing. Right? And so it's like a transit. No, because they both occur yes, but they both occur all together at the same time. So they would be
So they were at different times that I think they occurred here. You have a vertical line that's across. Some of those two sets are shared. Some subset not quite together. So the ones that ones that are sharing with other ones are kind of generalizations. Some of them are processes. You do the same thing. But anyway, so you're saying they're going to set just one pattern. I wanted into this is what we have to do. Sure. I mean, do you want to take this up and check it out? Okay. Both of us are like the same. Is everything? It seems like let me just explain it really the basic idea is let's say you have some SDRs, like some sequences. So these are SDRs, and then you have point cells up here, and what you basically have, they connect to some of the input bits, and
Like these are columns.
these are I understand these are like sequences in time, but it's think of this as like some input sequence, some pooling cells, and these may be in columns, they may not for this. So just like there's some initial connections, whatever. When you get an input pattern, each of these is going to get some input from these. And instead of just getting direct input that lasts for one time step, think of it as like activating something, and you end up with this like secondary messenger that kind of hangs around and keeps some channels open. So you get this.
So the synapse stays open.
Yeah, it keeps getting depolarized over time, and that builds up. And at some point, some of these are going to fire. They're going to get enough input that they're going to fire an action potential. They're going to inhibit neighbors. And so that's going to force sparsity, just like normal. But the key difference here is even whether you get inhibition or not, the secondary messages are sticking around because they have some half-life. And so this will become active, and then like its inputs will like kind of slowly taper off with some half-life. Then when we get new inputs here, they're going to contribute up here. And that's like the whole mechanism. So if you keep getting input here like 3 time steps in a row, you may build up a lot. And so you may be winning out really strongly for much longer. But eventually it's going to die off, and
so you're saying
it's going to take over.
In that model, then you still have a fixed sparsity. You don't increase the activation.
You can tell he's implementing some of the things.
Yeah. So I would implement this with fixed sparsity. It's easier to reason about. In the biology, we know nothing's fixed sparsity. It's like local sparsity.
Yeah.
But it's better probably just to do fixed sparsity.
Have you tried that?
Yes, kind of. Well, kind of. So one thing you can do is this has a nice property that you get input from infinitely far back in time, because it's a half-life. It's not like, what we did was we took, Sagan ran this experiment where he liked this idea, so he started running with it. So I said, just take this spatial cooler as is, union together the last 10 time steps, and feed that into the spatial cooler. And what you get is, we have these like roster charts where you have time going this way, and then you have column indices. Yeah, so in the temporal memory, it would just be like random, because it changes every time step. And when you do this, you get some like short little like things, right? And they die off. And what we were hoping, so I walked through this the way I described it to you guys.
You're converting time into space in a sense, and then
And actually, what's cool about this is, let's say you want to do spatial pooling. If you take this mechanism I described and you made it so that this half-life meant that things stuck around for roughly your time step interval, you basically have spatial pooling. But you don't have to get things at exactly the same point in time. You can get them just like with any of your senses, like it's not synchronized. Well, I shouldn't say that, because there are a lot of people talk about timing mechanisms in the brain, and so there's speculation about different synchronism. But basically with this, you don't need synchronization, is what I should say. And so what I was hoping with this mechanism is that now you need a learning rule. So because these things stay on a little bit longer, things that occur, they're going to be on after like the next thing happens. So this is going to become active. This is going to become active after it, even though it started becoming active before. But then you still get the heavy learning. So things further into the future are going to connect to this column because it was active after it. And similarly, like this may have caused this to become active, but whatever was active right before this will then also form a connection to that.
Sorry, I'm just, which direction are you talking? You're talking about proximal learning, right?
Yeah, it's all proximal.
So in the higher layer, learning proximal then goes down to the...
No. The connections for these connecting to these, with just the normal heavy mechanism, you should get, okay, so let's say you have some sequence here. and you have some column up here that's active for these 3 time steps, what you want is, and then you may have another one that's active for A and B, another one that's active like just for D, right? Like that would just, if you randomly initialize, that's what you end up with. But what you want is, if this is perfectly predictable, and you keep, and every time you see this sequence, like it's exactly the same, there's no noise, whatever. What you want is essentially some columns, whichever ones have the best potential overlap here, you want them to perfectly represent the sequence. So you want them to kind of like extend outward. And if I walk through it, it seems like it should do that. What we did was we took just the spatial pooler as is. We took a union of left pass things, fed that to the spatial pooler, and then tried learning and seeing if the learning would get this type of behavior, where the sequence is like, if it's perfectly predictable, you get a stable representation for it. And it got better slightly, but it wasn't as much as I would think. But I'm still hopeful that if you implement it the way I described it, that you would get that. But the other thing is, not only will you get the property where you get a stable representation for predictable sequence, you also get, like if there's subsequences here that occur in other places, you should also get recognition of that. And if there's like a sequence that's similar to this, you should get a representation that has some generalization and some specificity for the same reasons that you get in spatial. So that's the idea. Does that make sense?
Yeah, I think so. Yeah.
So again,
the learning you were talking about, learning is basically growing proximal synapses in the pooling layer, and
so I was just saying, so these give inputs to these.
Yeah.
And if you do heavy in learning, let's just say the representations up here are only active for 1 time step. So these things are active, they cause something to be active up here, and they reinforce that connection, right? Right? That's heavy in learning. If these things stay active longer, then things that occur, like the thing that caused them to become active would reinforce the connections, but also the things after them, they also start to connect. So that's how you get the representations up here to connect, like if the BCD, that's how you get that column that is active for BCD to also connect to E. And then you need to kind of relax the heavy rule and say, like, it's not the immediate thing right after it, but just in some period before it. And that's what would allow you to get back. So if you implement it like that, then theoretically things can extend their connections forward and backwards in time. It's just practically when you get that, and when you get it in an elegant way where you end up with good representations, or when you get like something winning out and running away or something, I don't know. And then also, can you do, like, you would still want like a potential pool to kind of like anchor the columns to some, well, in spatial pooling, we have a potential pool, and the reason why you don't have it at 100% is because otherwise you just get drift over time, and there's no like anchoring. So like one column, if you run the system long enough, it's just going to become something completely different. You lose all your learning. But by giving it a potential pool, it has a bias, and so it's less likely that it's going to become something completely different. It might shift a little bit, but it will
Just make your way back, guys.
So, yeah.
Thanks for that.
Yeah.
Thanks, really appreciate it.
I want to explain to you the space here because someone that actually explains this shit.
Yeah, well, I'll play around with it. You know, it's just,
Everybody ready to start?
So, what?
Okay, just one second.
You want to just meet in SF? Okay. Okay, yeah, so let's do that.
So, can you guys see?
Okay. So.
I'm just going to go easy with this. Hear me out. Okay, can you leave your answers? I'll get feedback here. Okay, so hi everybody, and thanks for turning up for this. So this is just something I've been working on for the last year and a half or so, and it's kind of finally came to fruition, and just kind of early summer. So this is, and it's still a work in progress, but I think it's step up, explain it to people. And so, okay, so just to really start off, I just want to show you a couple of things. And, it's just really motivated by the world that we live in. So I'm not sure if you can see this, but that's kind of the point of it as well. So what you just saw there was several thousand starlings in a flock being attacked by a herd folk. And there's a couple of things. First of all, each of those starlings is just paying attention to about 7 to 10 of its neighbors. And yet, they're able to react as a group of several thousand individuals to a single attack. That's the first thing. So that's what's known as a complex adaptive system. The other thing is that when we watch that video, we're able to see what's going on. So we can actually interpret this blob of dots as if it was a single organism reacting dynamically to a particular attack and emerging to form some sort of strategy. So there's actually several things going on. This is the hierarchy of these dynamics. This is not just the fact that the birds themselves are doing this, is the fact that when we look at that video, we can understand, even though we're looking at it 1,000 dots, we know exactly what's going on, why they're doing it, even though individually they're just reacting. That's the first thing. And the second thing then is the world of humans. This is a sport that we're very proud of. It's kind of a couple of thousand years old. I just want to show what this kind of highlights could some early. So you can see here that these guys are able to basically treat a piece of wood as if it was an extension of their bodies. They're able to do enormously complex, dynamical skills with a moving forward while running at full tilt, while being tackled by the way the score goes from and run over the shoulder for 90 or 100 yards. And this is a game that's been played in Ireland for the last at least 2,000 years. And it's something that you really need to be starting when you're 2 or 3 to achieve this level of skill. So the question is, what's going on? How do we do this? Okay.
couple of possibilities. One is to do something along these lines. And this is actually the philosophy and angle that we need to gain a goal in volleyball in order to do serve to serve, get over the net, and to deliver the ball at a certain point. The only problem is we forgot to drive. Now, this is one of the equations that you need to use in order to figure out what the coefficient, which is that KD is, in order to put it into the equations. And then, which for the same problem is the assembly problem. Serve and stand slow position. We need to take into account these things. These are the equations that we need. These are called differential equations that we need in order to figure out and what the expected spin is going to be on vertical orbits. So, possibly we're solving these differential equations, but it's quite an abundant sense. These things are already developed to the last. So what we actually do is split up this, and split up this, and split up this. So this is the real question. Like, what is our brains are doing in order to eternally be doing all these differential equations and all these computations, whereas in fact we do other things together. So really, there's a whole field of applied mathematics that's been developed since the 1960s, mainly because we don't have computers that can do all these calculations that don't require an understanding of differential equations, or if they do, you just plug them in and these libraries just set up. This is an example of low which basically rides a bike. It doesn't solve any equations. What it does is it just reacts to what's happening to the cell and to the bike. So it just collects for errors. This is a quick video by a guy called Steve Carr, which is one of the leaders in this field. So I'm just going to let this speak to itself. Just watch this one. It's quite true now. And so you can't hear it now. And
this is the Numenta chapter. The Numenta is an example of a couple dynamic system consisting of three differential equations, where each component depends on the state and the dynamics of the other two components. We can think of each component, for example, as these species: foxes, rabbits, grasses, and each one changes depending on the state of the other two. So these components, shown here as the axes, are actually the state variables, or the Cartesian coordinates that form the state space. Notice that when the system is in one lobe, x and z are positively correlated, and when the system is in the other lobe, x and z are negatively correlated. The manifold M consists of the set of all trajectories, and phi is the flow on M defined by the equations. M of t is a point on the manifold. We can view a time series then as a projection from that manifold onto a coordinate axis of the state space. Here we see the projection onto axis x, and the resultant time series for each displacement of x. This can be repeated on the other coordinate axes to generate other simultaneous time series. So these time series are really just projections of the manifold dynamics onto coordinate axes. Firstly, we can recreate the manifold by projecting the individual time series simultaneously back into the state space to create the flow. In this panel, we can see the three time series x, y, and z each of which is really a projection of the relation on that manifold. And what we're doing is the opposite here. We are taking the time series and projecting them back into the original 3D state space to recreate the manifold that butterfly attractor. There's a very powerful theorem proven by four statements that shows generically that one can reconstruct a shadow version of the original manifold simply by looking at one of its time series projections. For example, consider the three time series shown here. These are all copies of each other. They are all copies of the variable x. Each is displaced by an amount of tau, so the top one is unlagged, the second one is lagged by tau, and the blue one on the bottom is lagged by 2 tau. Higgins' theorem says that we should be able to use these three time series as new coordinates and reconstruct a shadow version of the original butterfly manifold. So let's see how this works. This is the reconstructed manifold produced from light to single layer. And you can see that it actually does look fairly similar to the butterfly chart. Each point in the three-dimensional reconstruction can be thought of as a time segment with different points capturing different segments of history of X. And the reconstructed manifold is then the library or collection of historical behavior of X. The reconstruction observes essential mathematical properties of the original system, such as the topology of the manifold and its diagonal exponents. More importantly, this method represents a one-to-one mapping between the original manifold, the butterfly tracker, and the reconstruction, and X, allowing us to recover states of the original dynamic system by using lives of just a single time series. Higgins' theorem gives us a one-to-one mapping between the original manifold and the shadow manifold. Here, we will explain how this important aspect of tracker reconstruction can be used to determine two time series variables that belong to the same dynamic system and are thus causally related. This particular reconstruction is based on the nice variable x. If we now do the same for variable y, we here we see the original manifold n as well as the shadow manifold x and my, created from lives of x and y respectively. Because both nx and my map one-to-one to the original manifold n, they also map one-to-one to each other. This implies that the points that are nearby on the manifold ny correspond to the points that are also nearby on the x. We can demonstrate this principle by finding the nearest neighbors of ny and using their time indices to find the corresponding points in mx. These points will be nearest neighbors on mx only if x and y are causally related. Thus, we can use nearby points on y to identify nearby points in mx. This allows us to use the historical record of y to estimate the states of x and vice versa, a technique we call cross-matching. With longer time series, the reconstructed manifolds are denser, nearest neighbors are closer, and then cross-match estimates increase in precision. We call this phenomenon convergent cross-matching and use this convergence as a practical criterion for detecting causation.
Okay, and so what that means in plain English is that you have a system which is operating in a chaotic region, which is okay, and what it means in plain English is that you have a system and it's producing a time series of a signal of some description that's generated from the system. And just using the time series, you can reconstruct the important dynamics of that system. Okay. That's effectively what the theorem in the middle of that video talks about, which is Captain's theorem, Taylor's theorem. Mathematically proves that this must be true of certain types of well-behaved systems. But what people since 1980 or so, in every maths department in the world, at the university, if you go down to what they're studying this. They're studying the fact that these things can actually be managed. So in non-analytical. So all you need is just data to convert this system. A suitable receiving modeling system can just extract the important information out of that and make forecasts and predictions, even though the system is being studied is highly complex, very chaotic. And so this is an important thing. There's actually a professor of applied mathematics at the UNC Meetup. I went through this entire thing with him, and he said, yeah, that's what we've been doing for the last 4 years. So he guarantees this is completely valid. This is all these guys have been doing. So the problem is that the mathematics of it is very complicated. So practically nobody else knows. But this is what all these guys are doing. So just to give you an example of that, this might be hard to see, but this is top chain translated into that version. So this is the same sort of plot as we saw in the last video. Just to let you see what's going on, this is a three-dimensional plot on that top-chain data. Okay, and you can see what it basically ignores. Okay, so this is the same sort of thing as you saw in the previous video. So it's a time lag X, Y, Z plot, the hot chain data. And to show you, I've done a similar thing where I've projected off graphs of and I'm glad to see what you're seeing next on. So you can see that there's graphs going on the X, Y, Z axes, where you can see what you expect from the hot chain waveform. So essentially, this is the same sort of thing. The idea is that you can, the theorem says that if you can basically project that data into a high-dimensional space, certainly in a region neocortex, it's going to give you a higher, the SDO is a higher dimensional reference. That you can essentially take in that data, absorb it, and merge it with the dynamics of the region itself. And perform this operation of these ways, being saying it's vital to have total dynamics. So that's essentially when you want to have the definitions of it's just like okay, so just to put that in perspective, so I'm starting very quickly. This requires now the prediction assisted CIA, this sort of problem where every cell has its own approximate damage, basically. And that's basically the one thing that is required. And I'm just going to very quickly go through this. So this is the vector version of our medical spatial field. This is important because and essentially what each column is trying to do when it gets a big forward input is it's trying to approximate that input. So the two green vectors here are close to the input, so they have a lot of overlap in the HTML sense, while these vectors here have much less overlap. These are the ones that participate in the SDO. So you can imagine that given an input, there's a kind of cluster of column representations that closely match that. Okay, so, and then transition memory is the same sort of thing. And then when those two are mixed, you get basically a current injection that is a mixture of feed forward input. And then that's just the time fly. And this is really the key diagram of how that works. So what do you see there? A number of columns, and in those columns, green ones are basically where cell has fired as predicted. Brown ones are and bursting columns. So you can see this is a sequence of the predicted columns going first, followed by the inhibition, and then followed by bursting columns. So if you follow the sequence of those, you can see there's a list of cells that fire first, the green ones, and there's a list of ones that are first. And those going into this sequence here, which is pyramid of cells, inhibiting cells, and then bursting cells, and spreading cells. Those form basically a vector, which is a inhibitor vector perpendicular to bursting. That's the signal that the layer of cortex is going to produce. Okay, so when you translate that back into this dynamical system thing, basically transition prediction is where a set of nearest neighbors are able to predict what's going to happen next in this kind of vector space of these dimensional concepts. And most predictions work very similarly, so this is I think where two predictions are taking place. And basically what we're doing is we're saying not only the wind regime or not the wind regime. So obviously this requires a number of different layers of the process. This is the sixth layer model that this extension of the theory involves. So the inputs, this is obviously very familiar, and Jack showed a version of this several times. But the important thing is that what's happening is that the inputs are coming in, they're into L4, which is modeling the transition dynamics, and then L23 is able to use a temporal filling and also taking in the bursting inputs. It's characterizing how that how the dynamics of the inputs are changing. And then that's feeding through to L5, which again forms a coupled dynamical system with the motor output. And then L6 is controlling all of these different activities by blocking or actually creating its own version of inputs. So for example, L6 can shut off inputs and then drive out forward, drive the entire rest of the region to stimulate forward. That's been working on something very, very similar. So that's really the central model that this kind of extension. So some of the things that this thing can do is obviously model states of transitions. And it can run a simulation forward by effectively forming a feedback loop between L6, L4, L23, L4, L6. So, and don't really go into top down. And you can also characterize the dynamics of the system. So, for example, the bird flock you saw when it was on its own, the right hand pressure, one type of dynamic, whereas when it was being attacked, it split into two or orbits for a certain bit. And we can see that, perceive that, and that's what happened. This kind of signal that is going to be shift of the dynamics. We also model the evolution of non-stationary systems as the same sort of thing. And that involves L23 go through the sequence of recognitions. And because of this chaotic signal noise, this is something again that comes very much to the coordinate space. And we also detect and measure causal relationships, that is referred to in the data calculation. And with CDR as being, it's actually called CDR causality, this metric. And you can do that directly. And you can also communicate between regions, and that's just simply about coupling the dynamics of different regions as well. So, for example, the fold network in the neocortex is basically about these things communicate with each other, and marks and rulings have very extensive word functions. And it's also about communicating with people, because that language has a time series of signals between the dynamic systems of the thoughts I'm having and the dynamic system of the thoughts that you're having as a result of the sleep. That's also the thought effect. Very much in the abstract, these guys didn't really have computation substrate to base this on. This is really the thing that I'm doing is to couple of the neuroscience models for these HTM to all the stuff that these guys do. And you can also obviously control your limbs, tools, and mechanical devices. You can do this in a very skillful way that involves taking chaos and turning it into neural cycles and making sure that it's much more predictable. And you do that using very low power and low bandwidth signals. Okay, so just to sum up, the hypothesis is that the brain is just like a digital computer. It's a universal symbolic computer. And I'm proposing that the brain is a universal ground systems computer. And we now have a really good mathematical model for it. And therefore, models of dynamics, there are 2 or 3 characterize the real world. They are 1 of those context. There are 5 acts in the world. And there are 6. Only this model is the operating system. So that's very much it. So there's some links to that. Doing the paper on that, which is like 75% good. Yeah, and everybody there. And Richard and Rob, Felix and Marcus, and they're very good at the feedback on this stuff. And some of the other people. That's really it. So, thanks very much. Okay, so the idea is that on all possible worlds, all possible things that would happen, only a very, very small number of those things do happen. So for example, if you drop a glass from 6 feet, it will smash into millions of pieces. Okay? It's not going to, those pieces will not be assembled. So the world only works in a small number of ways under all the possible relations. going to all these mathematical equations and but we really should look at that. Our brain something next time. What we do is we've done the small subset of things that really happen in the world. Okay? And we don't learn it by learning equations. What we do is we learn it by following the trend of how we see it actually happen. Okay? So what the mathematics shows is that you can just do that. You don't need to understand what the equation is going to be but the mathematics is just a thing that has mathematics role 7.5. But you don't need to know mathematics. All you need to do is watch it. And if you have a suitable apparatus in your head, then you can learn to build a model that works the same way. That's what this happens to brings mathematically for certain small subsets of these positions. But it turns out that these guys are not 20 years and 5 years. Every system you look at this works. So you don't need to understand the exact details of how this thing works. All you need to do is find some time series of chances and to be able to model those transitions. And you'll be able to make forecasts. So, for example, in weather forecasting, this is the type of thing that they use. So, supercomputers in weather forecasting no longer will be structural models. This type of prediction. They follow the learning. It's just use this kind of distortion and totally dynamic system. And so, the weather forecasting is really hard. This is traditionally state of the art in all of these countries. Nature discovered this millions of years ago. Nature discovered that it didn't have to start differential equations. It just had to build some way of sorting out the thing that information coming off these systems. And it just works. The mathematics that those just work. But what I'm saying is that that's why that brain is really good. One out of 4 and out of 2, out of 5, and out of 6. So the point is, you have to show the mathematics work and then let's say professors and they'll say, yeah, that's all the perfect. And then you just need to trust. I don't understand any more than you do on what this. I don't know the details of that. But I do know that this actually is a true fact. That this one thing that comes to measurements and stuff that you can learn how it works. That's exactly what we need.
Well, that's the fact you're hypothesizing that the brain operates.
Well, no, there's some negative dynamic systems, negative neural dynamic systems, reaction, coding pathway, and synapse to that. So,
Well, the way you define it is anything that operates
no, the dynamic system is just something that evolves over time, so some sort of deterministic way. Certainly, everything that happens in the brain is going to go to every level you look at. It's just that it's always too complex. The model is directly not. So, it's one day what I want to is how neuroscience is based on treating neuroscience as a complex process. So, what I'm saying is that it's not about information. It is step-by-step way and analysis, which is what the old-fashioned value puts in. That's a construct that we don't have to talk about. So every noun that we make is difficult, that's automatically. It's just this process of using a graphical system to model a graphical system, but graphical system. That's switch together, and then putting those together. These things just emerge. That has been more opinion on me. I never source code that we now have to take. No, one model is going to establish that's the yours. Yeah, so basically models in yours. So that's what it is. Algorithm. User space for they are models. So the dynamics of them are not directly models. Model dynamics goes a little simpler. They just have very, very small extension that uses the design. They are actually working on like they are working with data, so we must see but it's that's a very simple thing. That isn't it's very much very, very similar to what music is going to do. And music is able to model this stuff correctly. This is about taking a step by step, like snapshot by snapshot. And it's a simplification of what actually happens. Really, therefore, that's this is good enough to do it. You don't have to. There are discrete projects with that. But the dynamical modeling of the English is very, very complex. And that's what Jack was saying before. We don't need to model every single detail of every single process that they're going to figure out what's going on. Conversation. And the plan is to see and to show this happening using the step-by-step thing. I'm very confident that there's been a lot of work in doing this using dynamics and other types of systems as well. They don't have the complexity that HTM has. It's the computational kind of HTM has. I think that's something establishing these things. Well, I think that's already shown. All we've done is to show that it's probably not mathematical model per HTM. So, given the mathematical model, it's just basically derived from the algorithms. So, when the code is, you can see that you can get exactly that code. So, and when you do the learning on that, all you're doing is just casting the learning on that. Adjusting the elements of that and you're increasing subtlety a match between a single column connection vector and an input vector. And you just increase the match. So it's inherently stable and it's one of the results that show that when we have a system, you add in a k-unit and so argues that I think that's encouraging and start that first paper. So it's completely untimely conversation, but it's proofs of that, and it's also the information that it's happy to do in a motivated network and other administrators. So all those videos that I'm doing, once you can try to build stuff in mathematics, it takes you a lot. It's what that first step is really like. So I have to other people are pretty on this. We do those mistakes. There's nobody can have a sort of self-proclaimed to keep on innovating and doing folks that really good. He has an entire thing about how this type of model can be replicated without that complication. Using very similar ideas going forward. So top down feedback, and it's sort of doesn't hold that together, but this is those are crucial. But things are kind of showing that all of these things work. The actual custom sort of space is more and more. It's very it's sort of more and more like
The rest of the talks are not going to be remote. We're all going to be here. So I need 5 minutes of creation of it. I'm going to do Sutai, Felix, and Sutai is going to be whiteboard. Yeah, but he's willing to go over for 10 or 15 minutes current research state. Talk about what's happening. Anyone interested in that? See what's happening in research. So I'll just pull a whiteboard over here and set it up. And then we'll probably do Felix and Sergey and so you 5 minutes. You guys online.
So I'm going to give it a little flavor of what we're doing. Six and 9 months, and but we want to be No, there's a lot of. So there's a. Then we work on that. Other stuff. I work on that. And this is a really exciting thing. Then there is take a data set, providing it to HTM and SVM as well. Then we have it's a long time.
It's just, you can treat these just like slight things. Yeah, the model. No, it's an initial, very initial. It'll pick it up again, but it'll start temporarily. Give feedback. Have some label for the sequence or something. STR, recognize the sequence. It won't be scratch. That's yeah. So this is part of the. In order to do this, you need to have a stable representation. This kind of. It's layers of between. Layers okay, so we did feedback and this is being tested. And we know it's a lot of things. Another thing we did was we implemented another version of we did version last year. Another mistake he's finishing up. This is also here.
feedback experiment. Kind of question, feedback experiment with feedback signal on.
So when we did this, we kind of assumed that we would have done magic with color, and so there was a sample that's color. No, it assumes it. This one used to be called. Okay, so this, the code for that is there. Data. We don't know. There's still a lot of things here. In terms of for so we're focusing on focus now again these things. A lot of people are working about some of those things. So the applications that are using so here, what we're doing is we're taking audio feeding it into an HTM. And we get some signal take just the iOS and then we can run comparisons and see, okay, can you do that? Can you do something better than that? So people that pass the thing is when a data set, the university, lots of feedback from their employees about university itself. And what they want to do is basically browse that data set documents. Some employees complain, how should, given that, who else is complaining? That's like that where you really need to look for semantics and yes, the CIO, iOS DR. Trying to show the sequence. Like, and we put their employees so we really cool thing. We did this. It's also a great thing. On real. It's hard to get this here. One would be a lot more surprising. Look at that, actually, scenario graph from
Coming to the workshop tomorrow. So, Felix is going to talk next. Slides. Yeah, so and hopefully that has a higher level concept that is and a higher level concept which is connected to some other concepts like it's a higher level, not network. So the concept is that it's a lower concept, which triggers a higher level concept. Yeah, I mean, so yeah, so the part that we all have, it's my assumption is that we have an encoder for each sense that we have, and these encoders are not sufficient as a scalar, for instance, 1.1 is not the same as 1. It's a very different thing. But a scalar encoder to be very, very close. So a generic encoder is not the same. What natural language and not
So when we do this Excel thing, I'm coming after, I was predicting, I'm just going to do this. Well, I'm going to do it. Now, why does that matter? When the axon, this cell, connects to another cell, it will form a synapse. And synapses are, if you have a little medial occurring, what the postsynaptic cell do is when it's receiving that, it will typically receptors. It's both a heterotropic the longer lasting response. It's part of the single spike. All in the single spike, the postsynaptic cell is a very brief momentary motivation that if I admit a trio of this what will happen is we're only control by state up to 2 seconds. The cell says, hey, well, you like Literature about how often you all sell copies of the read versus not. Very well known fact, but our job here skill of question came up. Why do you care about this? I care about it why. It's another topic that is yeah, the notion of prediction and they like, oh my God, yes, I know this. Wait for it. I've seen this before. I know the difference.
Are there anybody else who wants to stand up and talk about anything? A little light talk about stickers. Tell me on that. Okay, so there's only one more, and it's me, and it's not going to be very scripted or organized. Okay, so I'm a data hoarder. I've been hoarding data for several years now. I really when I came into well, they had a big list of data sets to investigate, and then trying to find all this data. And so I'm going to talk briefly about where to get data, what to do with it, how to get it into HTM, and how to get it working. So, and this is like from a personal discovery standpoint, like yourself, how to get data yourself, but also how to help provide larger pool of data for the entire HTM community. If you're not aware of it, I'm creating a large pool of data that anybody in here can use to train their HTMs. You can help with that. So first of all, where do you get data? 4 years ago, it was a lot harder to get public streams of world data. It's quite a bit different. And something happened in the last 4 years. I think a lot of governmental policy changes were years earlier were finally like implemented, and we have these data projects where governments would say, okay, big initiatives to try and get municipalities and government agencies to open up all of their data. This is public data. It's our data. We should have access to. Does anyone ever work for government? Okay, so I have, and no one was very motivated to expose their data in any Zoom fashion for anyone in the public sector and the government situation. But luckily, because of these programs are trying to push this, make this data not only public, but available in an easily accessible way for API, not in any access to just put it on the other side of the firewall, which is typically what happens. So now there's a lot more public data. It gets a lot easier. To talk about a couple of ways you can find this data. I have recently been on my quest to find public data and put it into this streaming data framework that we call Whiteboard. And I've been plugging it there. I searched primarily and successful finding public data for scientific institutions that give government grants. They have this incentive to make the data public. I'm trying to find like research jobs for sensor arrays.
You're running a very heavy HTM workload with your application. For Cortical.
With which application? With
The natural language application.
Okay.
So how much is performance a concern for you guys?
For of the HTM side, it will become more and more. Because the more we integrate it, as soon as we, for example, use this new generation or to generate the document fingerprints, that can start to become an issue seriously.
So have you done any profiling? Do you know where your bottlenecks are?
I'm the wrong person to ask this. I suppose that people like Ray or so, they know this. I was about to start a discussion in turning the Java version into a Spark version, for example, to just have at least a little bit of maneuver room. But yeah.
So Spark, you mean like Spark servers?
Apache Spark framework. So we use this for our stuff.
What is Apache Spark?
It's an in-memory. It's like it's a stream processing mechanism. It's sort of the new version of Hadoop, if you want. And it's much easier to use.
So, which part of HTM would that be?
Look, with the whole, that's the kind of where you sort of put the whole implementation, you just put it into another framework to make it scalable.
I see.
But that's as far as my inside view of the code.
Okay, so is David working on Cortical.io as well? Okay, I did not know that.
It's stuff.
Okay. Where are you based out of? Are you in
Austria.
Austria? Did you fly in?
Yeah, I'm frequently.
Okay. How are you guys funded, if you don't mind me asking?
Venture funded.
Venture
For the
funded.
moment.
Okay.
Hopefully soon customer funded.
Cool, cool. Yeah, I mean, funding is really something that I work, I'm a PhD student and I'm really interested in HTM performance and scalability. I'm a hardware guy, so.
Hardware means what?
So computer hardware, chip design.
HDR.
Well, I have done that, but these days I'm doing more of like thinking about how algorithms map efficiently to a particular hardware platform. How to take an algorithm and map it to CPU, how to map it to GPU, how to map it to unconventional architectures. So that's where I'm coming from. And I'm pretty familiar with what the bottlenecks are of the baseline HTM platform, but I am interested in funding because I'm thinking
to do research.
Well, yeah, I mean, we are funded right now by the NSF to do research on HTM, but I'm thinking sort of long-term plans for myself. What I'm going to do after I graduate.
Professional plans.
Right. So I could just go join some. I mean, I'm actually interning at AMD right now, but yeah, it's not bad. It's dying, but it's not bad. I mean, I'm in AMD research, so AMD research is actually doing quite well compared to AMD. But anyway, it would be cooler to work for a really scrappy small company that is fighting for its life. And
I mean, the whole concept of AMD and von Neumann processors is about to die. So you're a young guy.
Right.
You should choose something that
Right. Well,
starts and
actually,
ends.
it's funny that you say that because my previous internship was with Micron, which is a memory company.
The 3D RAM.
Yeah.
Hyper
Well,
RAM.
it's crosspoint, 3D crosspoint memory. Yeah, that is really interesting. But I worked in the automata processor group, and
so yeah, I remember this is this hyper parallel accumulator, so to say.
Yeah,
sort of,
it can accumulate. So it's a non-von Neumann. It's very, very different. And my primary research is, well, no, it doesn't have a memory hierarchy. So the automata processor.
It has a different location for storing and for computing.
So it doesn't compute. There's no arithmetic units on it.
Yeah, but it does. What you do is you do Boolean combinations of the memory. That's in fact how you compute.
Yeah, I mean it's a big parallel lookup table. Basically, it's a stateful lookup table.
Yeah, but still you have to move the data from the memory to the lookup processor, or whatever you call it.
Right, but once it's there.
Yeah, but that's what for me the kind of phenomenon that interests me is where the data doesn't move at all. That's what I'm looking for.
Right. Well, it really depends on where you draw the line, right? So
no, you store when you sort of bring the data on chip,
right,
and you put it somewhere, and there it stays.
Right. So there are certain things the automata processor can do without moving the data.
So you can directly write into this register basically also.
You can't write. You can write to it from the outside, in which case it would be part of a von Neumann hierarchy. But you can use the existing memory to make inference steps, and then generate outputs that then again get read by some von Neumann machine. So the automata processor will never be able to run a Linux kernel or run a web browser or something like that. But what it can do is massively parallel lookups. So if you have many patterns that you want to match at the same time on one data stream, then it becomes really useful.
Match means what?
Match means just automata. So basically, it's state machines that processes input, and so if you can capture a pattern,
you send a pattern in and you get a pattern out.
So no, you send a pattern in and you get a yes or no out.
In terms of
So in a regular expression expresses a language, right? It's a collection of strings, right? So if you give it a string that is in that language, it will give you a 1. And if it's not in that language, it will give you a 0. And you can have many of those machines in parallel. So
that's typically my problem with these approaches. So I've superficially read about it, but I think that the hardware architecture has to be matching an algorithm. My impression is that many researchers in this processing, post-quantum processing, they first try to find a new architecture, and then they ask themselves, okay, what kind of algorithm could I run on this?
I completely agree with you.
And I think that's why, to me, the brain thing is so interesting.
Yeah.
Is because there actually the hardware grew along an optimizing algorithm.
Right. That's not my fault. Okay. So I didn't make the AP and then build it and then ask, what do we do? Because I think that's really backwards. Nevertheless, when someone comes to you with an unconventional hardware architecture and a bunch of money attached to it and says, go play with it.
I'm not saying that this is not interesting,
Right.
because you can learn a lot of stuff from there, and especially if you do a good research job, you should somehow end with a resume that says,
yes.
okay, this obviously in some way it makes sense, but it lacks the link between the algorithm and the hardware.
You totally hit the nail on the head. So as a computer architect, my ultimate goal is to produce a paper that has a list of architectural improvements that need to be implemented in the AP in order to make it
of this micron.
Yes. So I'm not. Actually, it's funny. I mean, you and Jeff are of the same mind because he raised the same issue. Is that I'm definitely not trying to put a square peg in a round hole, just to say like I'm going to get up there and sell the AP for HTM. I want to accelerate HTM. I want to make it more scalable, and I want to ask what applications can take advantage of that scalability. But we do that starting with HTM and then designing hardware instead of starting with hardware and then building HTM on top.
I mean, I'm currently concerned. I'm thinking in terms of a hardware model for our system, but not an accelerator for the HTM, but an accelerator for singularity, because that's at the core of what we do.
Accelerator for singularity.
So we generate fingerprints, so the 16,000 binary vector encoding the meaning of a piece of text, a word, a sentence, or whatever. And the business case is I have created 100 million fingerprints SDRs of my documents that I have in this large repository. And now I have this query. Someone typed in, I'm interested in blue birds with yellow, whatever. I take this and make a fingerprint of that. And now I say, okay, which of my 100 million documents comes closest to this?
Yeah. So the AP is a perfect platform for you. Because you have one input data stream and millions of patterns, right? So you want to take that one input data stream and match it against all of those patterns.
What is the stream in this case?
The stream is your queries.
Okay.
And your patterns are your SDRs that you
100 million, where do I put them?
You put them in DRAM.
No, then it has to be slower than my approach.
Yours is in SRAM? Or?
No, I don't use RAM any.
Okay.
Not any RAM. I create memory cells, smart memory cells, that first of all I have to do this in parallel. So my memory cell has to have 16,000 bits width.
Okay.
And this memory cell only knows to do one thing, that if it gets a second pattern into the, let's call it the data bus, it can count the overlap between the two.
Yep.
And this overlap count is then read out of a huge set. And so these memory cells, basically you put into the system as many as you want to store documents. So it's like memory.
Okay.
But it's always the same little circuit containing the 16,000 bits and the 16 entry
So I think you'd be really surprised at how similar the AP architecture is to
The point is that with my current design, I can query a system that contains any number of documents. So to me, it doesn't make a difference if I have 1 million or 1 billion documents. And the search time is always between 1 and 2 microseconds.
Okay.
Because that's the time 16,000 bits need to compare each other.
Okay.
Plus some time to read out the sequence, because that's also a problem. You want to have the result set sorted. So you want to have the biggest overlap first, the second biggest after, and so on. And so not only do I need to avoid piping the data around, but I need to avoid to be obliged to make a sorting afterwards, because any kind of sort takes cycles.
Right.
So I designed an interrupt-driven approach, where you have like each of the memory cells is linked to a 16-bit wide bus, so to say, and you have a counter on the bus that counts down from FFFF to 0. And whenever a memory cell has the same number of overlap, then the number that is exposed to the bus says, here I am.
Right.
And you start counting with all bits set.
Okay.
And like that, it takes just a handful of cycles, so to say,
Right.
to read out without sorting.
I thought you said you weren't a hardware guy.
I'm not a hardware guy.
Okay. Well, that's so. How is this model running? Is it?
So
do you have it in software, or do you have a simulator?
That's so to say the. For the moment, it's just in my head.
Okay.
I had the discussion a couple of days ago. I met a group of people who have also designed an acceleration board for vector compressions.
Okay.
But they have also, so to say, the problem that they need to pipe the data from some repository site to the board where you have then, I don't know, 100,000 conversion units or something like that, which, of course, I mean, we are speaking here of very high levels of pronunciation, so they are very fast. Yeah? But still, if I have the practical problem of having to compare a billion fingerprints, still every nanosecond counts, so to say.
Right. So tell me again how you're getting around the problem of piping the data from the query into the accelerator? Or am I not?
No, this is easy, because my query is just one fingerprint.
Right.
Yeah, so this one, and my memory cell has, this is a,
you can draw here.
Whiteboard.
Yeah.
The memory cell has one register that has 16K bits here. Yeah. And that is attached to the data bus.
Right.
That, of course, you can't sort of send 16,000. You send them by 16 bits or something. Yeah, but once you have to write the content in there, that's the data bus, and then you have a query bus that just latches in a second pattern, so to say.
Okay.
And all these. So if you say this is now my memory cell, and here you have the. So it pipes out, so to say, the 16,000 bits, and you have
this is the population counter.
Basically, whenever there is an overlap, it makes an request and whenever there is a one, you have here you shift this out, and here you have a counter that counts the number of ones that basically get there, which is the overlap in the very end. Yeah? And now you have here that one is, for example, 16-bit. A counter that basically comes here and compares this number with the number of the count. And whenever this is equal, then it sends out an interrupt.
Yeah.
Okay. And then you have some central processing stuff that manages to select the right chip to read out. Yeah, but you also have, of course, I forgot, that's the payload. Which is de facto a reference number to the actual document where this thing came from.
Yeah, that's an ID. Right.
Yeah, it's basically the, so in fact, yeah, you can regard this as a content address in memory.
Right.
Where this is a dynamic address. And that's the data basically. So that's it.
Yeah.
This data can also be read out whenever the instruct says it's your turn, tell me what your content is. And so this is the intelligent memory cell. And I want to create a VHDL model of this. To be able to basically deploy it on an FPGA if you just want to try it out to see if it works. Or I can go to Intel and say, yeah, do you want to license my IP and put it in your next vector processor or whatever.
So have you read the Atomic Processor paper, like the one that introduces the hardware?
I've seen a couple of videos where they explain it, but I didn't go deep. Yeah, because there is a number of criteria, and one is if the data moves. Then
what do you mean by the data moving?
Yeah, here you write the data in, and it stays there.
Yeah, that's exactly what the AP does. So here you have in the AP you have columns of measures, and basically what the AP does is you have an 8-bit, this is your lookup symbol. That gets decoded to 256 bits. Okay? And then each one of these memory cells has some bits that are stored in here, right? And when you give it an 8-bit symbol, this gets decoded into a 256-bit memory cell. And these patterns all get matched against this input at the same time. Right? So when one of
how do I arrange 16,000 bits here?
Right, you scan them in sequentially.
And you have to drive memory around.
Right, that's
a lot. Yeah, I mean, you basically slow down the process by 2,000 process cycles times 2,000.
But it only grows linearly with the size of the input. So the number of comparisons that you have to do is it doesn't the performance of the algorithm in this hardware setup is not dependent on the size of the input. So if you make your input larger, I mean, just imagine if these columns were taller. Okay, so
16,000 bit tall.
Right, 16,000 bit tall. Then you have exactly what you're talking about.
Then you would go in with 120.
Right. So what I'm saying is that the execution time of this implementation is not dependent on the number of patterns that you have. But it is dependent on the size of your input word, but only linearly so. Okay, so what that means is that you have a small constant that you have to wait. So it's not so. The important part is that your execution time is not growing quadratically or exponentially. Right. Exactly. So
here, what I claim is that the execution time can be at least theoretically reduced to the time it takes to make this AND here.
One cycle.
Optimally one cycle.
One cycle, right. So you have lots and lots of
in
these
reality
cells.
not, because you have to read it out, and so you have a little bit of overhead.
So I think you would find that if you built this in hardware, its performance would be exactly the same as the AP, because when you expand this comparator to be able to match 16,000 bits at the same time instead of 256, you would reduce your density.
My 16,000 is just a temporary standard.
Okay.
So this, you have to see this like in the old times, the processors had 8-bit.
Sure,
architecture.
yeah.
So here you can expect at some point we have a million, so to say, because we have how much is it then? Yeah, so 256 times.
So yeah,
256
again,
or so,
that really doesn't matter so much because your execution time is only going to grow linearly with the size of the input, but it's going to be constant with the number of patterns that you match.
Other thing because it's problematic. Here you can only do absolute overlap. Here in this architecture, I mean, it needs some additional stuff. It needs, so to say, additional shift registers. But I could make things like not only if you have some part of the SDR. Now, normally I have in one item I have a bit set here, and if the other one has a bit set here, in the current implementation, this is not overlap.
Right.
But if I start taking environment, so I say, okay, let's say for this bit I take into account all the 9 bits around, then I also count these one to see if there is some relative overlap. And this will be important at the point when we do generalization of the fingerprints. Yeah, so if you match two, so the two fingerprints are 128 times 128.
Okay.
And now you have a fingerprint A, and then you have a fingerprint B, and you do a matching, an overlay, so to say, and you count the number of overlapping bits.
Okay.
But you could do also a relative fuzzy overlap by saying if in one the position is set here and by the other it is here, I could say they are still overlapping because I have a topology here, so there is a specific arrangement, and so there is a neighborhood relationship.
Right.
Yeah? And to expand this design, doing this is adding 3-4 shift registers so that I can shift the different other columns next to the comparison, so to say.
Right.
Here, I don't really see how this would be implemented.
I mean, you can shift.
And that is basically one processor. So one chip is this whole engine.
Right. There's actually a lot more to it than this.
No, but from the logical point of view, that's so to say what one chip is supposed to do.
Yeah. So there's this. There's also some programmable digital logic, and then there's also
freely programmable. Like FPGA.
No, not freely programmable. So it's just simple ands, ors, XORs, NORs.
That I can route.
You can route into it. Yeah. But there are also counters. So the way that I do incidence detector
and you're using this to implement the FPGA.
Are you guys interested in cocktails or anything after
Yeah.
this?
I thought you were going to do that. So here is my very, very simple coincidence detector. Okay, so I have a set of,
so follow the interrogation. Follow it up.
I have a set of indices, right? So let's take this example, and then I'll number these 0, 1, 2, 3, all the way to 127, right? So I have these indices here. I put these indices.
So 127 is recorded.
Yes, you're right. So it would be 16K, right? Or minus that. So here we go. So this is encounter, and here's my input. Right? So what I do is I put these indices into this state, which is a column of memory. Okay, and for this SDR, I scan in all of the bits that are active. Okay, now while I'm scanning all the bits that are active, this state is activated, it remains activated by this keeper cell, and every time it sees a bit that it recognizes, it counts on the counter. Okay?
It's similar like
Yeah. So I have many. I have like.
Okay, so instead of using shift registers, you can do this with separate counters.
Yes.
Different offsets.
So now what I have is this counter has a threshold on it. Okay. So I can. So what this counter, what the number in the count, are the number of bits that overlap between the input and what I've programmed this coincidence counter or this incidence detector. Okay. So essentially, if you think about a proximal dendrite on a spatial pooler, I program it with a threshold, and when it's seeing some number of bits, doesn't matter what order, doesn't matter, you know, the early bits or the later bits, when it's seeing enough of the bits that overlap, it fires, and it indicates that that column is active. And then in the next, and then I have a set of these widgets for each cell in the CLA, and so I have two phases. I have a spatial pooler phase where I scan in SDR active bit indices, and then I have a temporal pooler phase where I scan in IDs of cells active in time step. So once this phase is over, all of my columns are activated, and all the cells in those columns are listening for IDs.
And where do you model the synapses?
So the synapses are actually virtual. So
where do you remember which neuron is connected, which dendrite or dendrite or branch even is connected to which other?
So that's all encapsulated by the IDs. Okay. So if you
update this, you have to, so to say, do this live whenever you have the correct ID in hand. So you have to be aware of when to update, when there is change.
When there are changes?
Yeah.
Okay, so with the current model of the AP, we can't do that, but in our minds, the AP can be written to like a DRAM because it is a DRAM. So the IDs of the cells that we respond to and we count can be updated just like writing to DRAM. So actually, what the automata processor model of HTM does is it stores the state of the CLA at any one time, and it's able to compute the next state.
It has an associated memory array that contains the state of the synapses.
Yes. So each one of these vectors contains the state of the synapses connected to this cell.
Yeah, this is definitely at least the most plausible approach I've heard. Because if you don't do this, it becomes a routing problem.
Yes.
You have to dynamically, while you are computing, you have to find
all bets are off.
Yeah,
all bets are off.
And that's what the IBM people try to do. Right. Working on neuromorphics stuff.
Yeah.
But this is really, I mean, there you go down to material science, chemistry, and this kind of stuff, because you need to find a substrate for chips that actually does.
I don't think that's the answer. I honestly don't think that's the answer. But this model is really impressive. So we're MISI. Does this mean anything to you? Multiple instruction, right? Multiple instruction, single data, right? So the right architecture that we are hitting on and the one that you're hitting on are both multiple instruction, single data architecture. Where you have a single.
Sorry, 10-second interruption.
Sure.
I'm sure there's synergy we're going off for drinks in like a minute.
Okay. Let's go drink.
You see, that's why some people study this and know what they're doing.
I'm just guessing about.
This is hardware. Hardware software.
Oh,
It's
right.
hardware.
Because I saw him shake his head.
My favorite topic. Yeah. I've been chewing on this white paper for a couple of nights.
Which one?
Oh, that's why I'm chewing on it. Otherwise, I would be like digestive. Skills like I gave it yesterday to Celia to proof it, and I just. Oh, wow. Yes. So in fact, I started and I started over, and now I merged two versions into one version because I couldn't decide which one to stick with. So I said, okay.
Take the best from both.
Well, actually, which was so to say, because they were like going off in two different directions. Here means over there. Yeah. 10 o'clock. With the 10 o'clock thing, I'm not sure. In principle, you should expect me. No, I mean, I've been trying to really not. With the real this was easier because all the nerds were kind of zombies anyway. And so I could just come in like 2 hours later and sign.
Now people know.
It's actually, it's running, HTM. So it's I know that makes total sense. And build application based on. We've been talking about a bit and it doesn't, that idea never incorporated online HTM processing, but just getting into a framework that's easy to consume and trying to provide incentives for companies to put their data up there and make it some value. But I think it's sort of starting to happen. Yeah. Right. From a 3D depth data from there's a game engine called Unity. And so somehow he just walk around the room and find out where all the balls are and somehow convert that into community, even into like create a virtual 3D space, and then you can do it. Yeah, is it? So he's
Going out to the bar.
5:30.
I know. I know. I can't do it on a Friday night. Yeah, I mean, sometimes I can go out Saturday night, but not Friday. By that time, I'm wiped.
Okay, we'll see you.
All right. Okay, thanks, Jeff. Well, it's not going anywhere, so I mean, it's not my
well, I manage the whole so I'm like, well, the past few months I've been playing this event tomorrow. So dealing with judges and submissions, websites. But yeah, I'm really a community manager and an engineer. Half the conference.
Yeah, currently we in our house is like startup house. So like this alongside to so many of our friends like they're here. So they're find out
Cool. That sounds like a fun environment. Nice to meet you. Goodbye.